Hello, welcome back. I'd now like to tell you about Lyapunov analysis for systems once we've linearized them. And in particular, I'd like to use our Lyapunov-based tools to try and explain roughly why, if the A matrix in the linearization of a system has all of its eigenvalues in the left half plane, then the system will be locally asymptotically stable. So what we want to try and show this using a Lyapunov argument. We're not really going to be able to do all the steps in proper level of detail here. We'll have to just sort of skip through things, and you're going to have to take quite a lot of things for granted, I'm afraid. There's a much more complete treatment given in the lecture notes, but here I'll just try and give you a flavour. So what are we going to be talking about? We're talking about nonlinear systems after they've been written in our linearized form. So we've taken x dot is equal to f of x, we've linearized it, and we've rewritten it as x dot is equal to ax plus h of x, where this is a nonlinear function containing all of our higher order terms. And that means that, so it's got all the squares and cubes and so on. And what that means is if we normalize this function h by the length of the vector x, this thing will go to 0 as we send x to 0. And you'll notice before we were always using this delta x variable to denote the deviation from an equilibrium point. Just to simplify notation here, we're just going to assume our equilibrium point is at the origin, in which case delta x is equal to x. So we want to analyze this with our Lyapunov tools, and we want to prove that the equilibrium point at the origin is locally asymptotically stable. And so to do that, we need, well, we've got our equilibrium point, we need a region omega, and we need a Lyapunov function v. And we're going to use as our region omega the set of points x such that x1 squared plus x2 squared, and so on, is less than gamma. So we're just going to look at some ball. So if this was 2D, this would just be the set of points inside a circle of radius gamma. So in 2D, this is what it would look like. And we're not going to specify what the radius is. In fact, in order to take advantage of this property here, we're going to have to make the radius smaller and smaller and smaller. We're not going to make it equal to 0, but maybe it's going to get arbitrarily small. But that's what our region omega is going to be. We've got our equilibrium point, so the next thing we need is a Lyapunov function. So what's a sensible class of Lyapunov functions to consider for this type of system? Well, if we think back to our lecture on phase portraits, we went and we classified what all of the phase portraits looked like around in the neighborhood of equilibrium points. And we got nodes and saddles and foci and all of these different classes. And just to sort of remind you kind of what they looked like. So for example, in a node, we had these two principal directions corresponding to the eigenvalues, and then the trajectories in the region of the equilibrium point kind of fell in. They were sort of a combination of the two directions, but one of the directions was faster than the other. So here, this direction is fast, so we quickly converge to this slower eigenvector direction, and then we sort of follow in, something like that. And then the foci, they were sort of spiraling, and we had lots of other different types. If you think, well, what would be a good shape of level set that would work for all of these different types of equilibrium point? Well, you might sort of think a circle would be good, or maybe even an ellipse would be even better. So in this case, imagine that we had a Lyapunov function whose level sets looked like ellipses. Well, that ought to do the trick, because all of the trajectories seem to be cutting through these level sets, and that would give us a v dot that's negative, which is what we would need to prove local asymptotic stability. And if you think, oh yeah, this might work for foci as well, or even if we change the direction of the eigenvectors. And in fact, it does work. So these, they're called ellipsoidal or quadratic Lyapunov functions, are what you need in order to capture they give an appropriate shape of level set, namely ellipses, to ensure that v dot is less than 0 as you come on in. So that's sort of the intuition. We need these ellipsoidal Lyapunov functions. So what would they look like? Well, probably the easiest one to understand is a circle. If I want a Lyapunov function whose level sets are circles, well, then I just want something on the form x1 squared plus x2 squared. It's quite common to put a factor of a half in here, and we're going to do that throughout. But the point here is that this Lyapunov function is constant if and only if we lie on a circle here. And then if I put like a 2 in here, now I would get an ellipse, and by messing around you can actually get all of the ellipses that you, any rotation of an ellipse and squishing of an ellipse. And messing around here corresponds to something very specific. It corresponds to picking v of x is equal to x transpose px, where this matrix P is from a very special class of matrices called the positive definite matrices. So P here is positive definite. And the notation for this is typically you use this like curly greater than or equal to. You don't use greater than or equals to because this is a matrix, but this curly one instead. So what are the various properties of these positive definite matrices? Well, the first one is that they give Lyapunov functions with ellipsoidal level sets. What are the other properties? Well, let's list out some useful ones, and I believe there's more details in the lecture notes. Property 1 is, given a positive definite matrix, x transpose px is greater than 0 for x not equal to 0. And this is actually the defining property of a positive definite matrix. A matrix is positive definite if it satisfies this condition. And you can already see why they might be good Lyapunov function candidates. I promise we were going to put a half in here. So that's the defining property. Property 2 of our positive definite matrices. What else? P is equal to P transpose. They're always symmetric. P3, if I take a unit vector, so V is now any unit vector, then V transpose P, V is greater than or equal to the smallest eigenvalue of P. So positive definite matrices always have positive eigenvalues, and if I use a unit vector V, V transpose PV is always larger than the smallest eigenvalue of P, which would be some positive number. I don't know if we need any more properties. We'll find out as we go. There's more details in your lecture notes. So we have a Lyapunov function, we have a region, we have an equilibrium point, we have some dynamics, we're now ready to go. So let's just start with our recipe for applying the Lyapunov theorem. First thing we need to do is check that v of x is equal to 0 at x is equal to x star. Our equilibrium point is at the origin, I put 0 in here, I get 0. Tick. 2, I need v of x to be bigger than 0 for x in omega and x not equal to x star. Well, x star is 0, and then this is the defining property of a positive definite matrix, is that this holds. So this is true, and it's true for any region omega. This would be true even if we went for a global result. But it's certainly true for a circle of radius gamma. And now we want, we're not looking for stability, so we don't bother with 3. We're going straight for local asymptotic stability. So we need v dot of x to be less than 0 for x in omega x not equal to x star. So this is what we need to investigate. So let's just go, let's do it. So v dot is equal to the gradient of v dot producted with the system dynamics, which when written in linearized form look like this. What is the gradient of v? Well, it's equal to px. It might look scary to imagine taking partial derivatives of something with a matrix in it like this, yeah, you kind of get used to these things, I guess. Maybe the easiest way to see something like this is true is to just look at this example here. So here we have that dv dx1, dv dx2. So that's the gradient. And this is equal to a half. And then here I get 2x1 and 4x2. And this is equal to 1, 2, 0, 0, x1, x2. And if I was to write this equation here, but with a matrix P in the middle, this is exactly the matrix I would use. So if you use this P and you write out x transpose Px, you get exactly this. So we know the gradient, we've got this, let's just keep on computing. So what do we get? Well, I'm going to do something a little bit funny. I'm going to put a 1/2 in here. So how do we find dot products? Well, we take the transpose of one vector and multiply it by the other vector. So we need to take the transpose of this vector and multiply it by this vector to get grad v dotted with ax. So x transpose p transpose ax. But it doesn't matter which one we transpose. We could have transposed this and kept that. And so let's do that. And that's why we've got this half here. So I've kept half by doing it one way and half from doing it the other way. This is just a kind of a common trick that you use when manipulating these types of expression. It's a good trick to learn. Fine, so we've done that. And now we just need this second term, but I'm not even going to bother to manipulate that. We're just going to leave it. So nothing has changed here. We've just explicitly written out grad v dotted with a of x, and we've done like a sneaky half trick to, we don't know why we've done that yet, but we have. And then here we've got just grad v dotted with h of x. Fine. And now I'm going to normalize by the length of the vector x. So I'm just going to, squared, in fact. So I'm just going to divide through by x1 squared plus x2 squared and so on. You'll see this doesn't affect whether or not this is true. It's just going to be a way to, what we're trying to show is that this term dominates this term, and this term is negative. That's all we're trying to do here. And normalizing this in this way is just a convenient way to show that this term is bigger than this one. So if we do that, I've now got a half, and I'm going to write v transpose p transpose a plus a transpose p. V. So what is v? Well, v is just the unit vector. So I've normalized x by its length. I had a squared here, so I can normalize them both. So v here is just a unit vector, and we're setting things up to use this property here. Fine. And then here I've got grad v. Okay, I will actually write it in. So that's now a times our unit vector. We use we use square root from here, and then here this is dot producted with h of x over x1 squared plus x2 squared and so on. So now we see where we're going. We know that as x goes to 0, this term here goes to 0. And what that means is that by considering gamma smaller and smaller and smaller, we make our region of points, so the values of x that we have to cover, smaller and smaller and smaller. And what that means is we can make this term here actually as small as we like. So this is some epsilon. Just by considering smaller and smaller regions omega, we can, whatever this is, we can make this as small as we like. And what do we have here? Well, okay, this is positive. We know we need v dot to be negative, so we just need this term here to be very negative, because then this plus epsilon will still be negative. So what would be good? Well, if we could somehow make this equal to minus q, where q was positive definite, So let's just say we're able to do that. Then we'd have V transpose QV plus epsilon, and this is less than, minus. And this is now less than or equal to minus lambda min of Q plus epsilon. So as long as we make gamma small enough, we can always make epsilon smaller than the smallest eigenvalue of Q, whatever this matrix Q is, and then we will have proved that V dot is less than 0 on such a region omega, and we'll have proved local asymptotic stability on that region. And you can sort of see how by balancing the size of the eigenvalues of Q off against the rate at which this thing is going to 0, you could maybe start to build up more of a picture of the region of attraction, but for our purposes, it's just enough to know that such a region of attraction exists. That's all. That's sort of the minimum requirement for local asymptotic stability. So we've managed to show that as long as P transpose A plus A transpose P is equal to minus Q, where Q is some positive definite matrix, then we'd be able to prove local asymptotic stability. And now this equation here, this has got a very special name. This is known as a Lyapunov equation. And you see, because P is equal to P transpose, we don't actually need this transpose here. So this thing here, this is called, this smells so good. This is a Lyapunov equation. And it turns out, and again I encourage you to consult the lecture notes, that this equation can be solved if and only if A has all of its eigenvalues in the left half plane. Yeah, maybe we can quickly try and build a little bit of intuition. Yeah, I don't know if it's worth it. There's a bit more detailed discussion of this in the lecture notes. Why might such an equation like this be true? Let's just assume that A has an eigenvalue decomposition. So let's just try and find a P such that there would exist a Q for which this would hold. So if A has an eigenvalue decomposition, and let's assume also that eigenvalue decomposition is real, then we could rewrite this equation as P t to the minus 1 lambda t plus T transpose. Let's assume the eigenvalues are also real. Lambda transpose, and then T to the minus transpose P. And now let's just set P is equal to T transpose T. And we substitute that in, and we get T transpose. And now you see this T will cancel with this T inverse, and I get a lambda. Yeah, I get lambda T, and then plus I've got a T transpose here. I've got a lambda transpose T to the minus transpose times T transpose is just identity. And so I've got T. And so this is equal to T lambda plus lambda transpose T. And now if I want to verify that the matrix is positive definite, I would just have to check that this, well, if I wanted it to be negative definite, I'd need this to be true. And now I just set Z is equal to Tx. And this becomes 2 lambda 1 Z1 squared plus lambda 2 squared Z2 squared, and so on. And now you see that as long as all of the eigenvalues are negative, then this quantity here will be negative. So you see a simple example. If the matrix A has negative eigenvalues, then we can build a P such that we can get a negative definite Q to come out the other end. And in fact, this is true in full generality. And again, I encourage you to see the lecture notes to fill in the details. But the key messages here are, when studying the linearization, we can use quadratic Lyapunov functions, and because we can always solve Lyapunov equations, this allows us to prove local asymptotic stability using the Lyapunov tools that we saw earlier.